This is free response question number 5 from the 2024 AP Calculus exam. This problem is primarily about tangent lines and implicit differentiation. If you appreciate the content, please give it a like. Consider the curve defined by the equation x squared plus 3y plus 2y squared equals 48. It can be shown that dy dx is equal to negative 2x over 3 plus 4y. Part A. There is a point on the curve near 2, 4 with x-coordinate 3. Use the line tangent to the curve at 2, 4 to approximate the y-coordinate of this point. First, we need to find the equation of the line tangent to the curve at 2, 4. To write a linear equation, all we need is a point and the slope. The point is given. It's the point of tangency, 2, 4. So all we need is the slope. The slope will be given by the derivative. So, dy dx at the point 2, 4 is equal to this, which simplifies to negative 4 over 19. So that is the slope. Now we can write the equation of the tangent line. Using point-slope form, the equation of the tangent line will be y minus y, so y minus 4, is equal to the slope, which is negative 4 over 19, times x minus x, so x minus 2. Since we are supposed to use this tangent line to approximate a y-coordinate, it's probably best if we get y by itself. So let's add 4 to both sides, giving us this. To approximate the y-coordinate at x equals 3, we will evaluate the tangent line equation at 3. You could stop here if you wanted to play it safe, or you could simplify. The y-coordinate at x equals 3 is approximately 72 over 19. Part B is the horizontal line y equal 1 tangent to the curve. Give a reason for your answer. Hopefully you have memorized that at a horizontal tangent line, y prime equals 0, or in this case, dy dx is equal to 0. So our strategy will be to find out if dy dx is equal to 0 when y is equal to 1. dy dx is a function of y and x. So before we go on, we need to find the x value when y is equal to 1. Substituting 1 in for y right here, we have this. That's x squared plus 5 is equal to 48. Subtracting 5 from both sides, we get x squared is equal to 43. Taking the square root of both sides, we get x is equal to plus or minus the square root of 43. Next, we evaluate dy dx at plus or minus radical 43, 1 to see if it equals 0. But dy dx is equal to plus or minus 2 radical 43 over 7, which does not equal 0. Y equals 1 is not tangent to the curve because dy dx does not equal 0 when y equals 1. Here's an alternative solution. We know that at a horizontal tangent line, dy dx will equal 0. So we can start by assuming that dy dx equals 0 and then see if it makes sense. The only way for a fraction to equal 0 is if the numerator is equal to 0. So we get negative 2x is equal to 0, and dividing both sides by negative 2, that means x is equal to 0. This curve will only have a horizontal tangent line when x is equal to 0. If y equals 1 is to be a tangent line, the point of tangency must be 0, 1. The question is the point 0, 1 on the curve? However, at the point 0, 1, the equation becomes this. Clearly, the left side of the equation does not equal the right side. So 0, 1 is not on the curve. In conclusion, we say y equals 1 is not a tangent because 0, 1 is not on the curve. Part C. The curve intersects the positive x-axis at the point radical 48, 0. Is the line tangent to the curve at this point vertical? Give a reason for your answer. At a vertical line, dy dx will be undefined. However, dy dx at the point radical 48, 0 is equal to this, which is defined. The line tangent to the curve at radical 48, 0 is not vertical because dy dx at radical 48, 0 is defined. Part D. For time t greater than or equal to 0, a particle is moving along another curve defined by the equation y cubed plus 2xy is equal to 24. At the instant the particle is at the point 4, 2, the y-coordinate of the particle's position is decreasing at a rate of 2 units per second. At that instant, what is the rate of change of the x-coordinate of the particle's position with respect to time? At the point 4, 2, the y-coordinate is decreasing at a rate of 2 units per second. That means dy dt is equal to -2. We need to find the rate of change of the x-coordinate. In other words, we need to find dx dt. To make dy dt and dx dt show up, we need to differentiate both sides of this equation with respect to time. So, starting with y cubed, this is going to be 3y squared, and then times dy dt. Don't forget the chain rule. On the next term, we're going to have to use the product rule. First, I will take the derivative of 2x with respect to t. That will just be 2 and then dx dt. The first time through, we leave the blue factor alone, so I'm just going to bring down the y. Then we put a plus, and we sort of go through it again. The second time through, we leave the yellow factor alone, so I'm going to leave the 2x, and we take the derivative of the blue factor with respect to time, so that will be dy dt. The derivative of a constant is 0. Next, we will evaluate this equation at 4, 2. Remember, at 4, 2, dy dt is equal to -2. So now we have this. We just need to solve for dx dt. Simplifying a little bit gives us this. -24 and -16 make -40. So we have 4 dx dt minus 40 is equal to 0. Adding 40 to both sides gives us 4 dx dt is equal to 40, and dividing by 4 gives us dx dt equals 10. Hey guys, don't forget to like and subscribe, but also if you found this video helpful, there's a lot more where that came from. You can click the upper link, which will take you to the whole unit playlist, or you can click the lower link, which will take you to the next video in the playlist. See you there.